Let's wrap up the material in Chapter 6 by putting together the information that we've learned about electron configurations with what we know about the organization of the periodic table. Remember, the Pauli exclusion principle kept us from putting more than 2 electrons in each orbital, and that really is what builds up this structure in electron configurations and allows us to connect with the trends in the periodic table and allows us to understand the periodic table. So for example, if we look at the alkali metals, the electron configuration for each has one s electron outside the corresponding noble gas configuration. This leads to the chemical similarities between these elements. Among those similarities are the fact that alkali metals tend to lose one electron when forming a cation. They all form +1 cations, which leaves them, after you remove this outer electron, with the especially stable electron configuration of a noble gas. That's why they only lose one electron and why they have that similarity. When we go to group 2A, the alkaline earth metals, we see highlighted in red here, they all have 2 valence electrons in an outer s electron. That's why they all form +2 cations in order to achieve the especially energetically stable electron configuration of the underlying noble gas. When we go to group 3A, the boron aluminum group, again, the valence electrons are highlighted in red in this table. Notice that the d electrons and the f electrons are not in red. Those are not valence electrons. Only the outermost s and p electrons outside the noble gas shell count as valence electrons. All of these elements have 3 valence electrons. Again, that accounts for the chemical similarity. Now you can very easily tell how many valence electrons elements have and what their outermost electrons, the subshell in which the outermost electrons are placed by looking at a periodic table. Here's an expanded version of a periodic table where we've put the F block in where the electrons would be added. So by reading a periodic table, you can see the order in which electrons fill the subshells without ever having to draw an Aufbau diagram to remind yourself of the order of energies. It goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Just by reading these off the periodic table, you can tell what the outermost electron, the subshell of the outermost electron. So this region in blue, the outermost electrons are in s orbitals. We call this the s block, the alkali metals and the alkaline earth metals, as well as hydrogen. Over here we have the p block. Outermost electrons are in a p subshell. That's why we call it the p block. Transition metals are the d block. And then the F block, usually written below the periodic table, are where we fill the F electrons. As we fill from 5s, 4d, 5p, come around 3s, then we fill the 4f. In the ordinary way of writing the periodic table, it looks like this. All we've done is pulled the F block down below just to make it more convenient to print the table. And here we have labeled the S block, the D block, the P block, and the F block, so that you should be able to tell at a glance if an element is over here. You know, without even knowing what the element is, that the outermost electron is in a p subshell. You know that immediately. In fact, it's not only in a p subshell, it's in a 6p subshell because it's in the 6th row. Notice that the first row of the D's, however, has a quantum number, principal quantum number of 3. N equals 3 is the first time that you can fill a D, so this is the 3D, 4D, 5D. Similarly with the F, the first row and the F's are the 4F's and then the 5F's. We can put this all together and use it to help write down an electron configuration without ever having to count the electrons or draw an Aufbau diagram, but just by looking at a periodic table. This is a much easier way of doing electron configurations. Let's see how it works. So if we want to find the electron configuration for selenium, first locate selenium on the periodic table. I haven't We haven't shown all of the elements, but we've identified selenium. Find the largest noble gas that is smaller than selenium. In this case, it's argon. And then we will write down an electron configuration in the following way. We write the noble gas in square brackets, and then we simply follow from this over to the next row. This row number 4, you can count down 1, 2, 3, 4. So 4s2. You just have to remember that when you go into the D's, the first D is a 3D. So 3d10, since that's completely filled, and the D subshell can hold at most 10 electrons. And then just continue over in the 4p, count over 1, 2, 3, 4. 4p4. Done. That's the electron configuration for selenium. For some elements, as they get big enough and involve the F electrons, you have to be fairly careful when you write this electron configuration. We're going to use the same idea. We're going to locate the element itself, bismuth, on the periodic table, find the largest noble gas that is smaller than bismuth. We're going to write that in square brackets and then just follow from there along the progression to write down the electron configuration. So doing that results in xenon in square brackets, and then following from here over to the other side of the table, we have 6s2, and here you have to remember that you follow along down to the 4f's, and then back up to where that F block was excised from and go through the 5Ds, and then we get over to the P block and count over 1, 2, 3, and we're at 6p3. And once again, we have an electron configuration. I've never counted the number of electrons. I didn't have to write an Aufbau diagram. I'm literally just reading it off the periodic table. So in terms of writing electron configurations, for sure, know the general rules for electron configurations and orbital diagrams. Don't confuse the two. Know what I'm talking about when I use these phrases, because I just don't give much partial credit for mistaking an orbital diagram as an electron configuration. And lastly, we're learning trends in electron configurations. That's the point. The power of trend is that once you learn the trend, you can make predictions about electron configurations without having to memorize electron configurations for each and every atom on the periodic table. That's too hard. We want a trend to be predictive. So the way I grade is based on following the trends. Even if there are some exceptions on the periodic table, the only ones I want you to know about are the 5 exceptions that we talked about last time. So let me just emphasize, you still need to know those. From our last talk, know those exceptions, and I showed those on a periodic table as well. But the 13 or 14 other exceptions, don't memorize them. All we care about is the general trend. That's what we're looking for.